Here you see the copper disc protrudes a bit off the outer circumference of the rotor. This comes to play in the contact system. Here we have two such end machines which will be joined on one shaft, as you see here. The discs being in direct electrical connection with the shaft makes this a series end machine. This 800-pound rotor must be housed in a completely non-magnetic environment. That is to prevent drag from reducing the efficiency of this generator. Both ball bearings and roller bearings are used to support this very heavy piece of equipment. Here is the bottom half of the liquid metal current collectors, or brush system. Within a copper bus bar, a slot is cut, as you see here, and the copper disc rides within this slot, along with a thin volume of mercury, which completes the electrical contact once the upper half of the copper bus bar is placed on the brush mechanism, as you see here. This is a terminal from which the electricity will be drawn. As I mentioned, this machine is electrically in series, so each terminal produces a different polarity of electricity. The end machine produces very low voltage at extremely high current, and is sometimes referred to as the unipolar dynamo, or homopolar generator, or Faraday's one-piece generator. The end machine is not to be confused with the Faraday disc motor. The end machine is an example of a generator which is not a motor. Therefore, the generating potential of an end machine is enormous. Here, in the early tests of the end machine, you observe a speed of about 1,000 RPM. As we took it up into the 2,000 and 3,000 RPM range, not nearly one-half its operating speed of 8,000 RPM, we noticed a problem with vibration, and this problem has yet to be corrected. So this machine, which we expect to generate 10 volts at 10,000 amperes at a speed of 8,000 RPM, has not yet been tested to its full capacity. Here you see the liquid metal being poured into the current collectors, and these are the cables taking the electrical output to a load resistor. This is W. Robert Kinchlow, Professor of Electrical Engineering Emeritus from Stanford University. He has written a report on one of Bruce D. Palma's earlier end machines, known as the sunburst machine, and we'll show you a videotape of a demonstration of that.
This tape is a documentation of an experimental machine, which is the reduction to practice of an idea we had about rotating magnets and whether they could produce electricity in a useful form. This is a big rotating magnet. Here, inside this fiberglass wrapping, is a solenoid. I think there's something like 2,600 turns of wire on here, and another half-inch overlay of fiberglass wrapping, so that when it's rotated at 6,000 RPM, which is its design speed, it won't fly apart. The magnet, one end north, the other end south. There's a disc on the edge of the magnet here. 12 brushes arranged around the edge, 4 here, 4 here, 4 here, and 4 on the bottom. That's 12 on the disc, and another 6 on the front of this plate and 6 on the back of this plate, which represents the 12 axis connections. Now, in order to test this machine, what we have to show is that we can rotate the machine and we can measure the current which is going to the drive motor. Now here, on this side of the room, is a 40 horsepower, 440 volt, 3-phase AC motor. On one of the phases is an AC ammeter. With that, we'll be able to tell the amount of power which is being drawn by the drive motor. And especially what we'll be able to tell is whether there's any change in the amount of power drawn by the drive motor, because it's overcoming the friction and the air losses here. When we run this thing as a generator, which means that we close the circuit and we allow the current to flow several thousand amperes indicated on these meters, and then we look at the meter over there and see whether we've taken any additional power from the drive motor in order to generate or liberate this amount of energy on this side of the machine. What we have here are the volts output and the current output of the machine. Now, this is going to be on the 2.5 volt scale, full scale. We're going to get 1 volt or so out of this machine. And this amp meter is a 0 to 800 amp meter, which is worked with these 2 shunts here. Each shunt is good for 800 amperes. 2 in parallel are 1600, and so this meter then reads 1600 amperes full scale. Now, in the event that the meter goes off scale, which it's going to do in our measurements, we'll use this voltmeter to measure the actual voltage going into the ammeter when it goes off scale over 800. So for each 50 millivolts on this meter, that is, yes? For each 50 millivolts on this meter here, which on this scale is 300, 200, 100 millivolts. So when it indicates this much on this scale, this will then be equivalent to 1600 amperes. And this will be 3200 amps, 3 times 16, 4800, and so forth, amperes. The product of the current times the voltage is the power being withdrawn from the machine, volts times amps. Now, when we take 5,000 watts out of this, in a normal generation system, we should have to see at least 5,000 more amperes flow into the drive motor, at least. In a normal generation system of 60% efficiency, we would take, if we took 5 horsepower out of here, we would have to put in maybe 7 or 8 horsepower into the drive motor to get that 5 horsepower electrical. Now, this machine liberates its energy right out of space. So for that, we don't have to depend upon the drive motor to supply any additional energy when we take the current from the machine. So when we run the machine, what we'll see is that we'll open and close this switch, we'll see the volts and the amps on these meters, and then we'll observe whether there's any increase in current to the drive motor. And that will be the proof of this experiment, because the ratio of the incremental input power there, as we close the switch here, tells us how much more power this machine is liberating from space than it takes to turn it. Now, our measurements at this very, very crude point say that we're doing something like on the order of 20 times. That is, we get 20 times as much power out of here as we have to put in there to generate that amount. And we'll demonstrate this on this apparatus. Now, the next stage here is we're going to turn this on and activate it, and we're going to get it running. And we'll photograph that. Before that, let's have a... What we're going to see now is I'm going to energize the magnet, and I'm going to ask Mr. Flowers over there to turn on the magnet power supply, which is through that wheel on the control unit. And then I'm holding this piece of iron near the magnet, and as he